Hello students. In the last class we have learnt the method of finding the position and nature of the image due to reflection of light through mirrors. And I told you people to practice the same for different cases. In today's class, first let us take some of these cases which will be helpful for our next discussion. Let us consider we have the concave and convex spherical mirror with P being its pole, F being its principal focus, C being its center of curvature, and PA being its principal axis. In the last class we have seen the formation of image when the object is considered somewhere beyond C and in front of a convex spherical mirror. So today let's go for some other possible situations. Let us consider we have an object placed between the focus and the center of curvature. Same way, let us consider one more such possibility, like we have an object placed between the focus and the pole of the given mirror, and in case of convex spherical mirror, let us imagine the object is placed in front of the mirror. So here in this case AB is the object. Let us consider the height of the object to be equal to HO. Now, to trace the position and nature of the image, let us consider we have a ray of light incident parallel to the principal axis. So we have a ray of light incident parallel to the principal axis. So as we have seen that whenever you have a ray of light incident parallel to the principal axis, after reflection from a concave spherical mirror, it will pass through the focus, whereas in case of convex spherical mirror, the reflected ray of light appear to diverge from focus. Same way, the other set of rays, you can consider any other set of rays to find the position of the image. Let us consider in this case the ray of light is incident along the focus. So a ray of light incident along the focus after reflection gets reflected along a path which is parallel to the principal axis. Same way, in the second case, let us consider you have a ray of light which is incident along the center of curvature. So if it is along the center of curvature, here we assume that it is somewhere along the center of curvature. So just try to observe and learn how we trace these reflected rays. So similarly, in case of the convex spherical mirror, let us imagine you have a ray of light which is made to pass along the center of curvature. So now if you have a ray of light which is incident along the center of curvature, which becomes the normal incidence, the ray of light will retrace its path. So this will be the direction in which the ray of light gets reflected back. Same way, in case of convex spherical mirror, the ray of light retraces its path like this. So now you can see that to find the position of the image, the method followed is we find the point where the reflected rays actually meet. So if we consider the ray of light, if you extend these two rays of light, you can see that these two rays of light intersect at a point which gives the position corresponding to a point A on the object. So let us call this position as A dash. Similarly, in this case, so if you consider a ray of light which is incident along the that is parallel to the principal axis. After reflection, it will pass through the focus. Now, if you observe these two reflected rays, on extending these two reflected rays, you can observe here, on extending these two reflected rays, they never intersect with each other. In such situation, the method followed is we back produce the reflected rays. So when we back produce the reflected rays, you can see that the reflected rays appear to come from a point which gives the position corresponding to a point A on the object. Let us consider this as A dash. Same way, in case of convex spherical mirror, the reflected rays do not meet at a point. So the method followed is we back produce the reflected rays of light. So on back producing the reflected rays of light, the reflected rays of light appear to diverge from a point, say A dash, which gives the position of the image corresponding to a point A on the object. So to find the position corresponding to the image of the point B on the object, the method followed is we drop a perpendicular from A dash to the principal axis. The point where the perpendicular dropped from A dash meets the principal axis, gives the position, say B dash, position of the image, say B dash, corresponding to point B on the object. So in this case, you will see that A dash B dash gives the image of the object. Let us consider its height to be equal to hi. Same way, in the second case, we drop a perpendicular from A dash to the principal axis. The point where it meets gives the image, say B dash, corresponding to a point B on the object. So A dash B dash is the image of the object AB. Same way, in case of convex spherical mirror, let us drop a perpendicular from A dash to the principal axis. The point where it meets, let us say it as B dash. As a result, A dash B dash gives the image of the object corresponding to the object AB. Now, so if you account for the nature of the image, in the first case, the nature of the image is real, as the reflected rays are actually converging, inverted, as it is formed onto the other side of the principal axis with reference to the object, and it is enlarged as the size of the image is greater than the size of the object. Whereas in the second case, you can see that the image is virtual, since the reflected rays appear to diverge. And it is an erect image, since it is formed on the same side, and it is again enlarged as its size is greater than that of the object. Whereas in case of convex spherical mirror, again it is an it's a virtual image, erect and diminished image. Now, you will see that from these above observations, it is clear that as and when you change the position of the object, the position of the image and the nature of the image changes continuously. And also you can check that if you fix the position of the object and if you change the size of the mirror, changing the size of the mirror here is nothing but if you change the radius of curvature of the mirror or the focal length of the mirror, again you will observe that both the position and nature of the image changes. Thus, we can conclude that the position and nature of the image always depends on the object distance or the position of the object. Similarly, it also depends on the size of the mirror that you are going to make use. As a result, we need to find the relation between u, v and f. U here refers to the distance at which the object is placed or the object distance. Similarly, v here refers to the distance at which the image is formed from the mirror, and f here refers to the focal length of the mirror. So we can see that if we need to find out the relation among these quantities, we have to repeatedly find out the relation in each of these cases. So to overcome these difficulties, we derive the relation among the object distance, image distance and focal length by considering any one of the following cases, and using sign conventions we modify the same relation so that it holds good for any of the following cases. Or in simple, we can say that sign conventions allows us to reduce the formulas for different cases into one single general formula. So this is the necessity why we go for finding out or using the sign conventions in case of reflection of light through spherical mirrors. So here we follow Cartesian sign convention, in which we always consider the pole of the mirror to be at the origin and principal axis to be along the x-axis of the coordinate system. So first let us learn what are these conventions, sign conventions, and how we make use of these sign conventions. So the first sign convention says that all the distances here refers to the distance of the object from the mirror, called as object distance, the distance of the image from the mirror, called as image distance, the radius of curvature, focal length. All these distances are always measured from pole of the mirror and along the principal axis. So remember, all these distances are measured from starting from the pole and along the principal axis, starting from the pole along the principal axis. This is what is the first sign convention says. Second sign convention says that those distances measured in the direction of incident ray are taken to be positive, and those distances measured in the direction opposite to the direction of incident ray are taken to be negative. So this is the second sign convention. Let us try to understand how we apply this to any of the given situation. The third sign convention says that the heights measured above the principal axis are taken to be positive, and the heights measured below the principal axis are taken to be negative. So let us see how exactly we make use of this. So here first let us realize the distance at which the object is placed from the mirror, that is like distance PB. PB is referred as your object distance, which we usually represent it as U with a letter like U. Similarly, the distance of the image from the mirror or from the pole of the mirror is referred as the image distance, always represented as letter V. Similarly, the radius of curvature, which is the distance of center of curvature from the mirror or from the pole of the mirror, that is CP, will be the radius of curvature, which we usually represent it as R. And lastly, we have the distance of the focus from the mirror or from the pole of the mirror, that is FP, is referred as focal length, represented as F. So now let us use this sign convention and let us try to understand how we apply it to the given situation. So in the first case, if you need to consider the incident ray, say here the incident ray is in this direction. This is the direction of the incident ray. So first sign convention says that all the distances are measured from the pole along the principal axis. That is, suppose if you want to account for the object distance, so you need to start measuring from pole to the object, pole to the object. So if you measure it from pole to the object and compare it with the incident ray, direction of the incident ray, they are oppositely directed. That's what is your second convention says. The distances measured opposite to the direction of incident ray are taken to be negative. So as a result, in this case, the object distance is taken to be negative. So object distance is negative here. Similarly, if you go for, say, your image distance, again, the first convention says that the distances are measured from pole along the principal axis. So we will be measuring your image distance again from pole to the image, which is again opposite to the direction of incident light. So therefore, image distance will be negative. So coming on to your focal length, which is measured from pole to the focus from your first sign convention, which is opposite to the direction of incident ray. As a result, focal length is negative. Same way, radius of curvature, which is measured from pole to the center of curvature, pole to the center of curvature, which is again opposite to the direction of incident light. Therefore, radius of curvature is negative. So this is what is your second sign convention, that is using first and second sign convention, how we account for the distances. Coming on to the third sign convention. So it says that heights measured above the principal axis. Heights here is, suppose if you need to measure the height of the object. So we are measuring the height of the object which is above the principal axis. If it is above the principal axis, it is considered to be positive. So height of the object by convention is positive in this case. Same way, the heights measured below the principal axis are negative. If you look at the height of the image which is measured below the principal axis, we take this to be negative as per the convention. So try to realize how we make use of these sign conventions clearly, because throughout our discussion in optics we will be making use of these sign conventions. So let us come into the second situation. Let us understand how we account for this. First, take the object distance. The object, which is the distance, is measured from pole to the object, whereas again the incident ray is in this direction. So they are opposite. Object distance is negative. Whereas if you look at the image distance, the distance is measured from pole to the image. That's what is your first sign convention says. And second sign convention says that the distance is measured in the direction of incident light. So if you measure the image distance here, which is in the direction of incident ray. Compare these two. They are in the direction. So in such situation, the distance is considered to be positive. So image distance is positive in this case. Coming on to your focal length, which is measured from pole to the focus, which is opposite to the direction of incident light. Focal length is negative. Coming on to your radius of curvature, which is measured from pole to the center of curvature, opposite to the direction of incident light. Again, radius of curvature is negative. Coming on to the heights measured, so you can see that height of the object here is above the principal axis, so by convention it is positive. Similarly, height of the image is also measured above the principal axis, so it is also positive. So coming on to the third case, you can see that again follow the same convention. You can say that object distance, the distance of the object measured from pole, whereas incident ray will be in this direction. They are opposite. Object distance is negative. Then coming on to the image, the distance of the image is measured from pole to the image, which is in the direction of incident light. So your image distance will be positive. So coming on to your focal length, measured from pole to the focus, which is in the direction of incident light. So focal length is positive. Radius of curvature, again measured from pole to the center of curvature. So radius of curvature is positive as it is in the direction of incident light. So coming on to the heights, using your third sign convention, height of the object measured above the principal axis, as a result it is positive. Height of the image, again measured above the principal axis, again it is positive. So try to realize these sign conventions, without which you will not be able to follow anything in your ray optics. So very, very important. Try to understand, consider different situations and find out how exactly you make use of these sign conventions. So here you can observe one more thing, that in case of concave spherical mirrors, the focal length and radius of curvature is always negative. So whenever you come across your concave spherical mirrors, you can directly say that focal length and radius of curvature is negative. Whereas in case of convex spherical mirrors, you will see that the focal length and radius of curvature comes out to be positive as per the Cartesian sign conventions. So whenever you come across convex spherical mirrors, directly you can take the focal length and radius of curvature to be positive.
Okay students, today we shall stop here. Again, I want every one of you to practice the method of finding the position and nature of the image in different cases and how you make use of these sign conventions in each of the cases. That will become very much convenient for our next discussion. Thank you.